Hello, everyone. On behalf of my team members, Diego Conterno, Tyler Michaud, and Alejandro Porcar, my name is Dylan Walter. We are Senior Design Group C, and our project is called the ADEPT, or Analog and Digital Effects Processing Technology. First, let's outline our goals and objectives for the project, starting with our project motivation. As engineering students, as well as musicians, our team is proposing a senior design project based around audio engineering, music technology, and sound design. Through this project, we can apply the engineering fundamentals we have learned throughout our respective undergraduate degrees into something we are passionate about. Closing the gap between technology and music, we aim to provide new alternatives for musicians who want to stand out and shape their sound in a unique way. We're providing a digital multi-effects solution that will have a creative impact not only on musicians, but also those with an interest in electrical and computer engineering. Next up, our objectives for the project. We want our audio effects unit to be as affordable as possible in order to compete with the many boutique guitar pedals available on the market today. Not only should an aspiring DIY enthusiast be able to afford all the components of our project, but it should also be easy to assemble and to use. With a simple user interface and parameter controls, the ADEPT will be foolproof. On the more technical side of things, we want our project to draw as little current as possible. This is important in order to maintain compatibility with the standard 9-volt, 100 milliamp pedal power supplies available today. We also want to make sure that we are only hearing the lush effects that our unit will apply to our instrument signal without any potential noise. We will ensure that the ADEPT has a high signal to noise ratio with crystal clear signal quality. Last but not least, we want the ADEPT to be reliable. By utilizing high quality components and a strong metal enclosure, musicians will be able to rely upon our product to function as it should, even when performing in harsh weather conditions or when stomping on this effects pedal night after night. For our project's requirements and technical specifications, we're utilizing a list that includes not only fundamental technological prerequisites, but also some more advanced aesthetic features. The technical requirements we have implemented in our design include analog to digital conversion, high input impedance, low output impedance, and standard connections that include 1/4-inch instrument cable inputs and a 9-volt center negative power cable input. Some of the aesthetic design requirements we have implemented include looper functionality, JTAG and SWD programmability, an LCD user interface, and dual foot switch functionality. Here's a block diagram depicting the high-level layout of our design. In addition to our individual responsibilities, we have also decided to divide our group into 2 specialized teams: the electrical engineering team that handles the hardware and PCB design, and the computer engineering team that handles the software and effects development. We find that this streamlines our workflow and strengthens our efficacy as a group. Next up, our hardware design. As mentioned before, our pedal will have dual foot switch functionality. This means that we will have a primary foot switch to turn the chosen effect on and off, and a secondary one that can be assigned various specialty functions. These functions include being able to start and stop the recording of an audio loop, or setting the rate of a time-based effect by simply tapping the foot switch at the desired tempo. For the primary foot switch, we will be utilizing a 3-pole double throw, true bypass, latching foot switch. For the secondary foot switch, we will use a single pole, single throw, momentary foot switch. In addition to these peripherals, we will also be utilizing 2 100 kilo-ohm logarithmic potentiometers to adjust both the overall volume of the pedal's output and the tone of the applied effect. The tone control is created by implementing a simple RC low-pass filter that will adjust the cutoff frequency of the signal as the potentiometer is turned, thus making the sound of the effect brighter or darker.
So let's start off with the MCU and why did we pick this MCU? We decided to go with the STM32F446RC. This is one of the many in the line of STM32's F4s. They have an exceptional performance since they're actually a 32-bit architecture processor. They also have a 180 megahertz clock, which is outstanding, and it definitely will help processing the bit stream coming from the codec. And although this microcontroller does not hold a DSP unit, it does in fact hold an FPU. floating point unit, which we are considering using it to implement our effects functions. So we're kind of relying on the floating point unit to, increase the performance significantly when it comes to our effects functions, as opposed to using an external DSP library. But of course, with this much processing power, we can implement both of these strategies, and we can test them out and see what we can get the best performance out of. So that should be exciting to see. And another feature of this MCU is the integrated configurable debug. This provides a high system visibility of the processor and memory through either a traditional JTAG port or a serial wire debug. This is pretty nice when it comes to debugging the processor itself and just finding out exactly what's happening. It is also a very cost-friendly MCU. Microcontroller, when it comes to DSP, are very high in price. For audio applications, this was about $7. So we really like this MCU. It kind of fit everything that we wanted to go for.
So in order for us to alter or modify the incoming raw guitar sounds, we first need to transform that analog signal into digital values that a computer can understand. Once modified according to the desired effect, we have to convert the resulting signal back to analog for it to be reproduced as sound. To achieve these conversions, we decided to use a codec, which is a device that contains both an ADC and a DAC. That is an analog to digital converter and a digital to analog converter, respectively. In our case, we chose the PCM3060, which is a Texas Instruments chip that is capable of 24-bit stereo resolution, as well as a sample rate of up to 96 kHz, which will be more than enough since it will stick into 44.1 kHz, which is really standard for audio applications. In order to communicate with the codec, we will be using the I2S protocol. This is a 3-wire interface which is commonly used when dealing with audio devices. This is because it is able to handle high quality audio data much better than other protocols. This interface really consists of only 3 pins: the clock or SDK, the word select, and the serial data. So for the serial clock, it's just a clock that we know. For word select, it's actually gonna tell you which channel it's coming from. So it's right side or left side, remembering that this is a stereo signal. And then for the serial data, we will actually get the actual data itself, the actual raw data.
Okay, so this is for our input and output buffers. So having an input and an output buffer basically helps us drive our signal, either going from the guitar to the pedal or the pedal to the amplifier. So buffers have a high input and output impedance. This generates a voltage-driven signal, meaning it doesn't take up too much current. So if we wanted to have multiple guitars or multiple devices cascaded onto our pedal, we'd be able to do so. So when designing our buffer, we chose an emitter follower configuration with a BJT. So we wanted to avoid using a buffer with a gain over 1, just because we didn't want to amplify our signal either going into the guitar amplifier or the pedal. So that's why we chose an emitter follower configuration, just because it has a gain of 1. So we used the 9-volt DC coaxial power jack. This type of jack's pretty standard among all guitar pedals. That and it's cheap, it's easy to use, and it's really small and compact. So for voltage regulation, we needed 5.5 volts, 4.5 volts, and 3.3 volts for step-down regulation. So we chose linear voltage regulators, and we chose voltage dividers to do this. So when we were considering how to regulate these voltages, we took 3 aspects into account. It was power efficiency, noise, and cost. So there's a bit of an inverse relationship between switching regulators and linear regulators. Switching regulators can be very power efficient, but they could also be very noisy from the switching itself. And linear regulators aren't very power efficient, but they're not very noisy at all, so they end up giving very clean power. So we chose to sacrifice power efficiency over noise. So that's why we chose linear regulators, just because noise wouldn't be an issue and it wouldn't affect sound quality. So we also made sure to configure our regulators properly. So basically, we went to the data sheets and we found the proper coupling capacitors for the inputs and outputs. And this basically helps to stop the transient response from switching on and off the circuit from damaging any components. So for a 4.5 volt, for biasing our buffer, we use a simple voltage divider for that. That just because we wanted to save money, and we also didn't want to have like an unnecessary voltage regulator taking up space on our PCB. So here's our schematic. As you can see, we pretty much split everything up into groups to keep things organized. You have our power section right here, our buffers here and here, MCU right here, codec, LCD, and our oscillator and flash memory. So for our PCB layout, we used AutoCAD Eagle because it's free. We don't have any money. So we use 2 layers for simplicity, that and proper grounding techniques. So the first layer is going to be signal tracing and power, and the second layer is going to be ground. So for the PCB dimensions, we used about 94 millimeters by 83 millimeters, just because we wanted to keep everything small and compact, and we wanted to keep it in a small metal enclosure for our final part of our project. So for our PCB layout, we also used through-hole and surface mount components. We used mostly through-hole just because it would keep things, again, simple, and that it was really easy to solder. So if we run into any issues later on down the road or anything like that, we can simply desolder it and make quick fixes along the line. So for prototyping and initial testing, we used an external power supply of 9 volts. We did this just to isolate any sort of issues that we would have, like short circuits or anything like that. So this was an easy way to analyze current when we were turning on our devices. So for our input and output buffer, we basically tested this by cascading them together. And then we used a function generator to basically emulate a signal out of a guitar. And we passed the signal through it, and we checked the input and output, and we basically checked for any attenuation, and that it would be about a gain of 1, which it was. It was about a gain of 0.98. So for our tone control, we used 2 potentiometers, one with a low pass filter and one with a high pass filter. We cascaded them together, plugged the guitar into the input and an amplifier into the output. And we were able to mess with the potentiometers and see how it would affect the sound quality. So we basically wanted to use it to emulate affecting bass, treble, and mid. So when we plugged everything in, it worked absolutely fine and there weren't any issues. So regarding our voltage regulator testing, it was pretty simple. One, we just wanted to make sure it was accurate. So we hooked up 9 volts from an external power supply. We measured the input and output to make sure it was accurate. So we had 3.3 volts right here, as you can see, at our output with the digital multimeter. And we also kept everything on for about 2 hours just to make sure that it wouldn't heat up unnecessarily. So we checked it periodically to see if there were any heat issues, just because heat conduction can cause damage to the component. And there weren't any issues with that. And here's the same thing for the 5-volt regulator. And that's all. That just leads us to software design.
All right, so for the software design portion of this presentation, let's go ahead and take a look at the overview. As you can see, some of these components have already been mentioned, so we're just going to focus the most on just the development aspect from a firmware perspective. Starting with in the integrated development environment that we're going to be using. Of course, we're going to be using the STM32Cube IDE. This is the IDE promoted by STM on their website. It is an advanced C++ development platform with IP configuration, code generation, code compilation, and debug features for the STM32 microcontrollers. It is also pretty similar in fashion to Code Composer Studio, which we have worked with for our embedded systems course here at UCF. Also, the STM32 Cube IDE has integrated in it the STM Cube MX, which is a different IDE that has this feature of pinout configuration, cloud configuration, and it's very nice. It's a very nice tool that allows the user to just configure the pins however they want, name them however they want, and it will automatically generate a code based on those configurations. Also, the STM32 provides a debugger mode, which allows the user to utilize tools such as build analyzer, static stack analyzer, integrated UART terminal, zero wire viewer. And it also has memory and memory browser views that can be used for updating and displaying memory data. And of course, it also has multi-OS support, which is pretty important for our group because a lot of two of our members of our group are using Macs, so that is pretty important. Moving on, we have the MCU overview. So this is kind of development and what the development entails for the MCU. Let's go ahead and start with a clock. So we decided to go with an external clock in order to prevent unwanted phase shift between the codec and the MCU. We're really using an external oscillator for the MCU only, rather than using the external clock for both the codec and the MCU. So we're actually making the MCU the master and the codec the slave, and they're talking to each other. The MCU is talking to the codec through an I2S mode for on the SPI line, and like I said, the MCU will be the master. We also decided to go with an 8 megahertz crystal instead of something higher, due to the fact that the 8 megahertz crystal are just more common on the market right now, and they're simply just more compatible with the STM32F4 line. So that being said, having an 8 megahertz external clock as opposed to a 25 or a 26 is not detrimental when it comes to the system's clock. Really what we're going to be doing is just setting the system clock through internal clock configuration that I showed you, the tool that you can see here in the slide. And basically we're just multiplying the 8 megahertz input clock that we're getting from the external, and we're just setting that clock inside the MCU to, somewhere close to 180 megahertz or so for the system clock. And this should be driving the peripherals. And as you can see, these are actually the peripherals at the end. At the moment, we have top 168 megahertz. And as you can see, we're using the HEC line right here, and this is the PLL over here. So let's move on to the external flash memory. So the reason why we're using an external flash memory is very simple. We're using it for storage, obviously. But let me elaborate a little bit on that. The recording audio frequency we're trying to reach is about 44.1 kilohertz with a bit sample rate of 16 bits. This is the industry standard. So the reason we say 16 bits in this case, and in the case of the codec, we're saying a 24-bit resolution. In this case, we're saying 16-bit because the flash memory itself cannot do more than 16-bit transfer. So anyway, we chose to go with a 16-bit. At the end of the day, a difference between 16-bit and 24-bit really is minimal to the human ear. So there's no much difference there. So why do we need 200 megabytes of memory? So let's look at the conversion. Here I'm showing you what 1 second of audio recording really means, and it actually translates into 88.2 kilobytes of memory required. And just so you have an idea, the flash memory of the MCU itself is 256. So really, we cannot use the flash memory of the MCU for this type of applications. Imagine if we're recording a 1 minute loop of a guitar. So as a rule of thumb, we say, for 1 minute, we're taking about 10 megabytes, So having 200 megabytes might be a bit of an overkill, but it also gives us a lot of room. So we're going to be using the external flash memory to record audio, and also we can store libraries in there, and we can store more effects. All right, so let's talk a little bit more about our sandbox or the playground. Having a reliable test bench for firmware. As you can see, this Nucleo board is kind of where we're trying to develop most of the code, and this is a fast way to test our code from home. In the scenario that we find a roadblock with the hardware on the prototype board, we can still continue development on the firmware on the dev board. It is also pretty cheap. It costs us about $20, and it has the same processor that we're using on the prototype board. Obviously, it's not the RC, it's the RE, but same architecture. Is an F4, so there's really not that much difference when it comes to migrating the code from the Nucleo board to the prototype board.
This is a list of some of the different guitar effects we plan to implement on our device as of right now. In here, we can see listed common and classic guitar effects, such as chorus, delay, and distortion. I'm not really going to take time to explain each of these at the moment, since it is pretty difficult to describe sound. Instead, I can tell you how we plan to implement these effects in code. In order for us to actually reproduce these effects with code, it is necessary to perform a series of operations on the digitized sound bits. In order to achieve this, we will be utilizing the Synthesis Toolkit library, or SDK library. This is an open source audio signal processing library written in C++, and it was designed to facilitate rapid development of audio and music synthesis software. This library contains several classes and functions to produce a wide array of different sound effects, which will be really useful for our purposes on this project. To explain how we'll implement the SDK library into our design, I will use the delay effect as an example first. There is an entire class dedicated to the delay effect that we can see on the figure on the right. In it, we can find specific functions that allow us to produce the delay effect, but also many others to modify specific effect parameters, such as changing the timing of the delay, in this case. Other effects that we have in mind, such as distortion, do not have a dedicated class to them per se. However, by combining functions and by adding our own twist to them as well, the SDK library can provide us a lot of value. So when it comes to the user interface, we're going for a very simplistic menu. This is similar to traditional market guitar pedals we have seen. To the left, there's a figure of the physical pedal prototype with some of the knobs and buttons that we included. So once the device is turned on, the user will see something similar to the top right figure. This will be the main menu. In this screen, we will see at the top a little add icon. Below it, the effect selector. Using the dedicated selector wheel, the user can scroll through all of the included effects. When he's decided on one, he can click on it, and that will take him into a specific effect menu, something like the bottom right figure, where the name of the effect is shown, as well as certain sound altering parameters that are specific to that effect. The user now will be able to control the values of these parameters by using the top 3 knobs seen here on top of the screen. This is what we're sticking for now. And as more desired functionalities are implemented, such as the tap tempo function, we will create some dedicated interfaces for each.
All right, so for the administrative part of our presentation, let's start off with the project management tools that we're using. Notion is our central project management tool. We use it pretty much to set deadlines, keep track of progress, hold ourselves accountable of the tasks we are required to do. And it is also pretty good for taking notes of our meetings. Google Drive, we're using it for storage of files, large files, PDFs and stuff like that. And also Google Docs is huge. And of course, Discord for communication purposes and quick file share.
When referring to the cost of this project, we have actually done a pretty good job of staying within the budget we proposed ourselves in the beginning. Some of the components that have been more costly have been the PCB at $60, understandably, the external oscillator at around $20, and the input and output audio jacks, which altogether cost around $18. This added up brings it to a total cost of around $142 with 68 cents as of right now.
Okay, so for our progress percentage, as you can see, the research documentation and design has already been completed. So pretty much what's left is on the hardware side, any roadblocks that are presented, we definitely have to solve that as soon as possible, since we cannot definitely test our firmware on it. However, on the development side of things for the firmware, we have started developing a couple of things on the dev board, and that's why you see a couple of percentages here. Now moving on to the next slide. For current issues and future solutions, we're currently facing a roadblock, which is the JTAG connection to the prototype board. We have recorded our box and updated it to the forums, and we have also addressed this issue by communicating it to different people in the innovation department that could potentially help us figure it out what's going on with it. Aside from that, the LCD configuration and backlit contrast, this is pretty much an issue that can be solved by simply soldering connections on the PCB using a Mac wire for now, but this will definitely be fixed on the next prototype version. And rotary encoder is able to only rotate in one direction, which is not much of a problem, but considering we can solve this problem through the firmware, we are coming up with a different solution on the software side, but it can also be solved through solder to the connection of the PCB using a Mac wire. And for the software development aspect, we are definitely going to start implementing libraries, creating the LCD menu so we can test that last the last bug that I mentioned, and of course mapping the knobs to the effects parameter, and we need to come up with a trial effect to really test this out. So that's it for the current issues and future solutions. I hope you guys liked our presentation, and if you have any questions, please let us know.